In this video, we'll be talking about the concept of a phasor. Phasors allow us to do things like divide complex sinusoids. We've already established that the vector representation is useful for addition of sinusoids. We're now going to go one step further into complex numbers, and we'll show how it might be relevant to do so. As a motivating example, let's take Ohm's law. We know that the resistance is the voltage over the current. Now this is still true whether we're in DC or AC. However, in AC, V and I are sinusoids and things get a little bit more challenging. Say for example that V is Vm, and typically we say Vm to mean the magnitude of V or the amplitude of V, and cosine of omega t. And let's say I is Im cosine of omega t plus some phase phi. Now, a couple things to remember. Our omegas are the same, but the phases and the amplitudes are not. Now we still have that R can be represented as V over I, but this is now going to be something a little strange. Vm over Im, and all I'm doing here is just dividing the functions, cosine omega t over cosine omega t plus phi. Now what? I'd like to avoid having multiple resistors, or I beg your pardon, multiple cosines. So what do I do? I'm going to be honest with you at this point. There is a derivation for the following formula. I'm not going to present it in these lectures. What we're looking at is something called Eulers Formula. However, it's not a particularly interesting derivation. We're just going to have to take it on faith for now. It is very useful to represent a sinusoid as follows. If my sinusoid is A cosine omega t plus phi, I can represent it as the following complex numbers. A times e to the I phi multiplied by e to the I omega t. This is Euler's formula, and again, I'm not going to be deriving it here. When all of the frequencies are the same, and we know that, we typically ignore this part. There are some interesting interpretations of what that part actually means. But for the most part, we're going to represent this sinusoid as its magnitude times e to the I phi, where it's understood that when we go back into an actual sinusoidal representation, so when we go from the complex to the sinusoidal, there is that omega t term that we still need to consider. For our math, it makes it easier to ignore it. So now we can go back to our original example. R is V over I, and that's now given as Vm over Im, and then e to the I times 0. Remember that initial phase of the cosine for the voltage was 0, over e to the I phi. This is just the division of an exponent. So that gives us Vm over Im e to the I phi with a negative because we're subtracting. Now, we said we could go back and turn this into a sinusoid, and in fact we can do that quite quickly. R is Vm over Im, so I'm keeping the magnitude. Cosine, I now put that omega t term back in because cosine is a function of t, and minus phi, and that's because of that minus sign there. You might be looking at this and saying, what? How can I have a resistance that is a sinusoid? We're going to get to that for the entire next unit. Right now, understand that if the voltage and the current are both changing, and the resistance is just the ratio of the two, it makes sense that the resistance might be perhaps a time-varying quantity. Now, Let's take this as true for now, and take a look at the quantity a e to the I phi. This is called the phasor. If you're wondering, it's a phase vector. Here's your phase, and remember we were talking about the fact that this can be represented as a vector. Phasors make it very easy to multiply and divide sinusoids. In fact, let's now summarize some rules. Let's say I have two phasors. A, and I'll put a little bar underneath to define the phasor, is the magnitude of A, e to the I phi, sorry about that, e, and the phasor B underscore is magnitude of B e to the I, and let's define its phase as theta. Then the multiplication of these two, and this is just using laws of exponents, is the magnitudes multiplied together, e to the I, and then the phases added together, phi plus theta. Similarly, if I divide them, it's the ratio of the magnitudes, e to the I, phi minus theta. So these two relationships are showing us that it is very easy to multiply or divide. And when I say very easy, I don't mean that it's actually simple. We had to learn a lot to get here. What I mean is, if you compare that to the effort we'd have to do to actually divide the functions, this is far faster. Now, if we're going to add those phasors, we actually have to go back into the vector form, or what is sometimes known as the Cartesian form. To do that, the Cartesian form is as follows. A is the magnitude of A, cos phi, times the magnitude of A, sine phi. B is the magnitude of A, the magnitude of B, cos theta, magnitude of B, sine theta. And if I add them together, I get magnitude of A cosine of phi plus magnitude of B cosine of theta, and magnitude of A sine of phi plus magnitude of B sine of theta. Similarly, if I were subtracting, that would be a minus sign. So, we now have almost all the tools we need to work with sinusoidal inputs. Our next step is going to be transitioning and learning about how we can start talking about how these things work in circuits. What is power, for example? What is resistance? What does it mean now? That'll be the topic of what's coming next.